All right, so we're going to continue with learning about some properties of vectors. So one thing we can do here, as we learned, we can add vectors together. But another thing we can do, we can multiply a vector by a scalar. So let's say we have a vector, for example, let's say here's a vector A, and let's say it has a magnitude of 3. And let's say it's in a positive x direction. By the way, I can just do this. Plus x, this is the direction. If I then multiply the A with, let's say by some scalar quantity, let's say 3 times A, what it does, it makes then the magnitude, 3 times more, so 9, but it doesn't change the direction because this is plus 3, technically. That means this will be like, 3 times longer vector. I can also take the A and multiply it, for example, by minus, 1/2. What it does, it makes then the magnitude, you know, a half. Let's say we're using this original one, right? So let's say 1.5, and it also changes the direction because of this negative. So then this will be something we will get. So that's kind of what we can do. We can always multiply the a vector by scalar, and we can change the magnitude and the direction depending on if there's a negative there or not, for example. All right, so and generally another thing we can do here is instead of multiplying vector by a scalar, we can actually do a product of two vectors. So the product of two vectors, which is let's say you have vector A and vector B, can actually give us two different results depending on what method we use to do this calculation. Because technically there are two different ways. You can take two vectors and multiply them together, but what we want, let's say, the answer to be a scalar quantity. So then we use this, what we call a scalar product, or another name is a dot product, okay? And let's say you have vector A, let's say vector B. So, and the theta here, the angle between those two vectors. So again, here I'm connecting them by their tails, right? For example, but if I multiply those two vectors, A times B, right? And I want the answer to be a scalar, and there are some physical quantities where by a product of two vectors you do get a scalar, like energy. We will learn about that later on. Then we use this scalar product. The answer here is this: it's a product of their magnitudes, A times B, and times the cosine of angle between them. So if I have the magnitude of A and magnitude of B, I multiply those, then times the cosine of angle between them. Sometimes we want the answer to be a vector quantity. In that case, we use a vector product, A cross B. So we sometimes call this a cross product. That's why I use the word cross. So A cross B. This is in a way similar if you have the A and B and the angle between them. So this becomes an AB sine of theta, which is different from AB cosine theta. So it's AB sine of theta, plus there's the direction involved over there, which we then use what we call a right-hand rule. All right, so generally this is much simpler. This is a little more complicated. So we're going to learn about that in later chapters. But you need to kind of understand that you can also do that, and there are some ways of getting a scalar and a vector depending which, let's say, product you are using. Right. Now, the very important thing about the two-dimensional vectors, when we're going to be seeing a lot of two-dimensional vectors, actually, we will see that it's not easy for us to, for example, add two-dimensional vectors. It's not difficult graphically. We can do that graphically. So let's say if here's one vector, you put another vector, and then this is the resultant, right? So the graphically is not that bad. But for us to try to actually calculate the value of the magnitude and the direction of the resultant, I can no longer just add their, let's say, magnitudes and things like that, because those vectors are two-dimensional. They have, X components and Y components and so on and so forth. So that's why one of the things we're going to be learning here is how to find a two-dimensional vector's components, and then be able to replace this two-dimensional vector in terms of its components. All right. So let's imagine that what we have here is this vector A. And vector A, you can see here, is a two-dimensional vector because it has a length, let's say, that is equals to A, which is its magnitude. And it has a, polar coordinate theta, right? The angle that is neither 0 or 90 or 180 or 270, which are those extreme, let's say, axes, right? So this is some theta, I don't know, let's say some 30 degrees, right, with respect to positive x. Remember, because we're going counterclockwise, it's positive. So that's a two-dimensional vector. So for example, if I have another two-dimensional vector and I want to add them together, I can't just add them directly. It doesn't work like that. That's why the vectors can get, vector addition can get very complicated if you have, several vectors that are two-dimensional. Calculation can get messy. What we do here is this. Taking any vector, we can find its components. And by components, I mean its projection, sort of like, let's say, on the x-axis. That means you can see, right? I look at its projection, and this is its projection on the x-axis. We call that ax. And it's another vector, right? Pointing in a positive x direction in this case. So you can say that this one, let's say, has a magnitude of ax, and it has a direction. By the way, I can put the direction as theta equals 0 degrees, and you know where it is, right? In which direction it is pointing. I can also find the projection of this vector on the y-axis, which is this guy over here, right? Let's say this guy over here. So for this one, I also can represent this vector ay, in terms of its magnitude, ay, and the direction as 90 degrees. Okay. That means, in a way, you are restricted to have the x component always either 0 degree or 180 degree, to the right or to the left. And y component of any vector is going to be either up or down, or 90 degrees or 270 degrees. So that's something that you should try to remember in terms of the components. Now, what I have here is then, I can, for example, take the vector ay, and remember, I can move a vector as long as I keep the same magnitude, same direction, it's still the same vector. So think like this, if I move vector ay right here, you can see, right, it has the same length and same direction as the vector ay that I have over here. So technically, this is the same vector ay. One thing you can see here is this. This shows you how A is related to its ax and ay components. Won't you agree that this is basically nothing but tip to tail, where you have ax vector and then ay vector, and if we add those two together, we would connect them like this, right, tip to tail, and then to get the resultant, we would go from the point 0 to all the way to point 2, right? And that's what A is, right? A is basically kind of like the hypotenuse of the triangle. That means component sum, ax plus ay, is equals to vector A. And that's going to be true always. Sum of the components, a vector sum of the components of any vector, will be equals to that vector, that parent vector. And, which means that I can potentially replace this vector A with the sum of its components, which is like, okay, so the question is, why am I replacing one vector with two vectors? Well, because that one vector is a two-dimensional vector and it's complicated to work with. Those two vectors that I have, the components, are each one-dimensional vector. And I can easily work with them because if I have another one-dimensional vector, x component, I can add them together. Another vector with a y component, I can add y components together, because any two vectors on the same axis can be added together algebraically. Any two vectors on the same axis in vertical direction also can be added. We can do that. And you can see that in a, let's say in a more complicated problems, this is the only way and the best way to solve the problems. Yes, there's a graphical method, but its graphical method gives us just approximate values, not exact values. All right, anyways, you can see that we are basically creating a triangle, which is AX to be its adjacent component, right? Or adjacent side, AY is its opposite side. And using basically, again, Pythagorean theorem, we can see that X component is nothing but A cosine theta. And Y component is nothing but A of sine theta. That means in this particular case, what I have here is um, we can say that vector A was broke down or decomposed into its components, right? And AX right now always going to be X component of any vector, always going to be along the X-axis, and X component of any vector, Y component of any vector going to be pointing along the Y-axis, right? So for example, then another thing it's important to understand is, for example, this vector A is in the first quadrant. That means the X component here should be positive, and this should be positive because it's in the first quadrant. If you have a vector, for example, in a, let's say, second quadrant, then X component is negative and Y component is positive, and so on and so forth, right? So this is negative X, negative Y, then positive X, negative Y, right? Positive X, positive Y. Those are in terms of the signs of the components. That means all the components will kind of follow the, the quadrant rules. All right, so so the previous slide showed us that if you take a vector A, you can decompose or break it down into components. And the components are basically, so going to be given with those two equations. Think like this. This is going to be true if theta is with respect to x-axis. So this is thing like this. This is true if the theta is with respect to x-axis. But for example, what if I have this theta over here? Let's say I'm given this theta. Okay, I can still do that. So this is then going to be my y component. Then this is going to be my x component, right? And in this particular case, right, imagine I'm not using this, but I'm using, let's say, this one over here. For this particular case, then AX is the opposite side actually to the theta, and AY is adjacent. So then technically AX will be a sine of theta, AY will be a cosine theta, because AX is opposite, AY is adjacent. Okay, now what is the difference? Well, nothing. So let's say this was 30 degrees, then this will be what? This will be 60 degrees, right? And if I do here is as A times sine of 60, well, over here is A times cosine of 30. Well, they're the same thing. So that's why, in a way, see, we're not changing anything about this vector A, right? Vector A is still 30 degree with respect to positive X, or 60 degree with respect to, positive Y, right? Negative 60 technically. But still, what we have here is, I'm going to get same thing. I'm going to get exact same answer because vector A is unchanged and its component values, either written in terms of sine or cosine, will not be changed again. All right. Oh, very important thing. So this was, let's say, if you were given, thing like this, if you're given A and theta of A, right? So this is theta of A. Then you can find the components. Also, one thing we could do here is this. What if it's other way around? What if we're not given A or theta A, but we are given, let's say, AX and AY? What do we do then? Well, remember, what we do then is this, understanding this, those AX and AY are nothing but the, sides of this vector, right? So let's say this is AX, this is AY, right? Then I can use the Pythagorean theorem to find the magnitude of A, which is the hypotenuse length, size, right? AX squared plus AY squared. Then find the theta of A, which is using tangent of theta. That means you use this if you're given, think like this. If you're given A and theta A, you can find the components. But if you're given components, then you can use these equations to find the magnitude and direction of the parent vector. This just, again, tells you, what I already went over in terms of the components to be positive, negative, depending in which quadrant they are, right? So first quadrant plus plus, second quadrant x is minus, y is plus. Third quadrant, both of them are negative. Fourth quadrant, x is positive, y is negative. Right? Because you can see, right, when any vector that you take, when you break them down, see, pointing to the right, positive, pointing up, positive. That's for the first quadrant. Second quadrant, pointing to the left, negative, pointing up, positive. So this one, for this vector, pointing to the left, x component, and pointing down, y component, that's why it's negative, negative. And same with the fourth quadrant. All right, so you can see, right, the components of a vector can be expressed in any convenient coordinate system. Because one of the things we can do here is we can actually tilt our coordinate systems depending on what type of problem we have. For example, if you have a, let's say a problem like this, where the object is going along the flat surface, then I can take this to be x, this to be y, just like what we would do. But for example, if the object going down an incline, and here's the object going to go down an incline, I don't want to use this coordinate system again, because when the object going down an incline is going to be then two-dimensional motion. But what I can do here is I can tilt my coordinate system to match the surface, the incline. Then this will be my x, this will be my y. So then when object goes down an incline, it's going down my only horizontal axis. So it's a one-dimensional, and I can tilt my axis like this, and we're going to be doing a lot. This is going to be done a lot, especially when we get to let's say two-dimensional motion. All right, so let's look at then some examples. So we have a vector that has a component, horizontal component ax equals 22 meters, and a vertical component ay equals 13 meters. What is the magnitude of this vector? Well, you can see right here is a drawing for that. And this is basically showing that those two vectors are the components of vector A. And remember what I said, right? Given ax and ay, then we can equals ax squared plus ay squared, which means then 22 meters squared plus 13 meters squared, and we will get 26 meters. That's the magnitude. One thing to remember is this. When you have two components, two numbers, right, that you're using in this equation. So this is 22, this is 13. The answer will always be closer to the, and actually larger than the largest number you are using. That means, see, 22, the number will be always a little bit larger, a little bit larger than the largest number, which is now 26. If let's say this is 22 and 3, for example, then it will actually be a little bit more closer to this number 22. Maybe like in this case, it will be 23 or 24 or something like that. So the idea here is this. You can always expect what to get, which is the magnitude from the components, right, will always be a little bit larger than the maximum value of the components, or the largest component that you have. Part B, it says, what angle does the vector make with the positive x-axis? Well, in that case, you can use this tangent of theta, where it's going to be y component over the x component, and this will be then converted into inverse tangent of calculation, right? So you can find the theta. So this will be 13 meters over 22 meters, and then the theta will be 31 degrees. Right. That means it will be 31 degrees with respect to positive x-axis. Generally, when you're giving me the theta of a vector, I imagine that everybody would always think of that this is a reference with respect to positive x-axis in a counterclockwise direction. So you have to make sure then when you're giving me the theta, for example, see here's a direction of another vector. Let's call this vector B. And let's say you're given the components. Well, the components will be like this. This will be its x component, this will be its y component. So when I move the y component here, this tangent of theta, this equation, right? That equation will actually give me then this angle. And you're going to get maybe like, let's say, negative 31 degree, for example, right? So let's say negative 31 degree. Imagine that, let's say the x component here is negative 22 and the 13. So what you would get here is negative 1. Well, that's because it is 31 degrees clockwise from the negative x-axis. Remember, counterclockwise is positive, clockwise is negative. So that's why it's negative 31. But remember, when I want an angle, I want with respect to, so with respect to positive x-axis, because that's the reference line. So what you do here is you need to find this angle over there. So this is what I want. Well, all you have to do is just take one, because we know that from here to there is 180, and then this was then 31. So 180 minus 31 will give you the right answer. Where is it? 149. So it should give you then the right answer here. Okay, because that's the angle that I want. I want the angle with respect to positive x-axis. All right, so here's another example, the y component of plus 9.6 meters. Then A makes an angle of 32 degrees counterclockwise from the positive y-axis. All right, so let's try to see what we have. We have a y component, which is given as 9.6 meters. So this is the y component. So AY. And let's say 9.6 meters. And then we're given that vector A, the only information else is vector A is 32 degree counterclockwise from the positive y-axis, which means that vector A, the resultant vector, is like this, somewhere over here. All right, so this is vector A. Now, okay, so then the question here is this. What is the magnitude of vector A? All right, so then what we need to do here is we need to find, the component of vector A. X component, so X, what is the X component of vector A? All right, so one of the things, and there are a number of things we can do. So I recommend you start writing, making a table of what is given to you and what you need to find. So you can say, all right, so AY is 9.6 meters, and A is basically on, we have that unknown. The only thing is like theta of A is 32 degrees. Let's say, right? But, this is 32 degrees right now. But in any case, one thing we can do here is this. Remember, we can still assume that if that's the resultant, I can represent my triangle like this, and this is being the X component of the vector A. All right. Now, what do I have here is this. I have that triangle because that's the 32 degree I'm given right now. So if I want to find right now what is AX, I can see that I can use inverse tangent, or like let's say tangent of theta, because for this triangle, tangent of theta relates the X and Y components. But remember, tangent of theta is equals to opposite over adjacent. Opposite in this case is AX. Adjacent is AY. That means what I can do here is I can find AX by saying, all right, so it's AY times tangent of theta, which is then 9.6 meters times tangent of 32. And we can find the X component then to be negative. Well, this is going to give us 6 meters. But we can see that A is technically pointing to the left. So that means AX equals negative 6 meters. So you have to be, that's why you have to be careful in what you're doing. All right, so then what is the magnitude of A? Well, that's now easy because we have both X and Y components. So this will be negative 6 meters squared plus 9.6 meters squared, adding the, components like that, and we get 11.3 meters. All right. Okay, so here we have finally, some two-dimensional calculations, vector calculation. So let's say right now we have this. We have vector A that has a magnitude of 40 meters and point in the direction of 20 degrees below the positive x-axis. A second vector, a B, has a magnitude of 75 meters and pointing in the direction of 50 degrees above the positive x-axis. Okay, so that means we need to then sketch the A, B, and vector sum of A plus B. All right, so let's do this. So here's vector A, here's vector B. Here's our coordinate system first. All right, so then Vector A is right here, right? It's 20 degrees below the positive x-axis. And then I have vector B, which is 75. See, if I'm saying the length of A is 40, length of B is almost double that, 75. So that means I have to make this one like a little bit longer. So this is B, all right? And then what I have here is, this is basically 50 degrees. I have to make sure that this is, more or less about 50 degrees. Now, what I also have is say C equals A plus B. That means I want to see which one is A plus B, which is some vector C. All right, so I showed you about tip to tail method, but there's also another one technique that we can use, and this is known as a parallelogram method, graphically adding vectors. The parallelogram vectors takes those two vectors A and B, connects them at their tails, and then generates a parallelogram like this, right? So parallelogram, and then the resultant vector will be a diagonal line like this. So this is then the resultant vector. This is then vector C. All right, so that's, C equals A plus B. If you do tip to tail method, right? So for example, if you move the B over here, you see would have get the same thing. Okay, so this is then the graphical method. Now we're going to use a component method to find magnitude and direction of vector C. At least right now by this graph, we can get some information already. See, for example, this is the direction of C. I can predict that probably to be about 30 degrees, right? You can see, right? It's roughly about 30 degrees above positive x-axis. And I can see that vector C is a little bit longer even than vector B, which was 75. So I predict vector C to be, so let's say this is my prediction. Theta C to be about 30 degrees. And the magnitude of C to be maybe about, anywhere like, let's say, I don't know, maybe 85 or something like that. Again, so I'm predicting that. Could be a little bit different, but at least this is what I expect values to be more or less. All right, so then what I have is this. There, I'm going to show you sort of like 4 steps that you need to do in order to get this answer. And then any type of vector calculation like this, again, involves these 4 steps. Step 1 is doing this graph, actually, because it allows you to estimate things. Step 2 will be to make a table. Here's what the table will look like. So here we're going to have our vectors. Sorry. This is going to be then the x-axis. Here I have y-axis. All right, so my vectors are A and B. Remember, what I'm doing here, I'm basically saying A plus B is equals to vector C. But I cannot add vectors B, A, and B together directly because they're 2-dimensional vectors. I can do them graphically, but not, analytically. So you cannot do that. All right, so what we do here is then this. We then take all of those vectors and break them down into components. Recognizing that vector A has a direction with respect to positive x-axis, means x component is the adjacent one. So for the x component, you can see, right, for x component of this vector A, I can write as A cosine of theta. And then the y component is A sine of theta. But then I recognize that vector A is in the 4th quadrant. So x is positive, y is negative. Then for B, again, theta of B is given with respect to, with respect to x-axis. That means x component is adjacent. So I can write this as B cosine theta and B sine of theta. B is in the 1st quadrant, so this is plus, this is plus. Now, why am I doing this? Because A and B cannot be added directly to get C. But x component of A and x component of B, they can be added directly because both of them are horizontal vectors. That means if I add those together, what I will get here is the x component of the resultant. Y component of those 2 vectors can also be added to one another. And I will get then the y component of the resultant. Which means this table allows you to organize your vectors, get the correct signs, and then get to part 3, step 3, where you get 2 equations. One, how to calculate the x component, which is basically the general equation like this. It's x component, sum of all x component of all of your vectors. In this case, it will be then a cosine theta plus b cosine theta. Well, this is theta A, this is theta B. Well, I can calculate that. Cx is equals to, well, A here is 40, then cosine of 20 plus B is 75, then cosine of 50, right? All of their values. Then I get Cx, the component, right, to be 85.5, sorry, 85.8, sorry, meters. Okay. For step 3, I also get another equation, and that's how to calculate the y component, which is generally the y component sum, like this. Well, for me, the y component then happened to be actually the difference, because the a component, the y component of a is negative, so it becomes negative 40 sine of 20, then plus 75 sine of 50. And if I plug in those values, I'm going to get 43.8 meters. Because here's the thing, component method allows you to do this, allows you to calculate those two things. So see y component, allows you to calculate x and y component of your resultant. Because now, remember, those are the components of my resultant. And remember, if you look at the component signs, both of them are positive. What does it mean? That means it's a, component of a vector in the first quadrant, which agrees with my graph. Now let's calculate magnitude and the direction of the resultant finally. And that's where the step 4 comes in. Step 4 is now where I calculated my component in step 3. Now I can use them in step 4 to calculate the magnitude and direction. And we learned that, right? If you have the components of a vector, then you can use this equation to find its magnitude, which will be square root of 85.8 square plus 43.8 square. And we get the C to be 96.3 meters. And that's more or less agrees with what I had expected. So I said 85, but this is about 96, right? So again, I'm not very off, right? So I said it will be longer than 75, and it is. Now the next step will be to find the direction, and that's just inverse tangent. And that will be, let's say, 43.8 over 85.8, and then we get 27 degrees. And that also agrees what I was expecting, which is 30 degrees. So that's the thing. Any type of vector addition, this could have been even like, A plus B plus D plus, K or thing like that, right? Doesn't matter, you just had more things to add. But any type of vector addition, you just basically use this four-step approach. 1 is the graph, 2 is the table, 3 to calculate components, 4 to calculate the magnitude and the resultant, magnitude and direction of the resultant. All right. So one thing we do here is to simplify our presentation of the direction of the vectors. We're gonna start using this unit vectors. So unit vectors are just 3 vectors. Each one has a magnitude of just 1. They have no units. That's why it's unit, right? They have just magnitude of 1, they have no units, but they're point in a very specific directions. So for example, vector I hat, we call it I hat, points in a positive x direction. Vector j hat points in a positive y direction. Vector k hat points in a positive z direction. That means, for example, I have a vector A, and I know that there is an x component. So remember, this is a y component, right? And a z component. In a vector format, I can say this. It's A equals AX plus AY plus AZ. Because, if I take vector A, it's a 3-dimensional vector, I can break it down into 3 components. But I can also rewrite this in terms of taking AX and multiplying by I hat in no way changes the ax as a vector, but it gives a direction. It makes it clear that, for example, this vector ax is a horizontal vector, because anything, like, let's say, think like this. So for example, ax is 5 meters. Say 5 meters I hat clearly tells you that's a horizontal vector in a positive x direction. So let's say that negative 5 meters j hat. Well, this means this component is a vertical component because it uses j hat, because j hat is a vertical vector unit. But negative means just it's actually in a negative y direction. And let's say plus 2 meters k hat. This means that there's another component 2 meter long in a positive z direction. Okay. That means just a way of representing our vector in terms of unit vectors, which makes it a little bit easier to read, a little bit easier to present the directions of the components of the vectors. So here's then again what I can do, right? So instead of saying vector A equals AX as a vector plus AY as a vector, I can just replace AX with magnitude of the AX and times the I hat. AY vector is magnitude of AY times J hat vector, because I hat and J hat vector doesn't change the, anything about AX. It just basically gives it a nice way of representing direction. Okay. All right. And then this just tells you that, for example, if you have a vector and you add a b vector to a vector a, so a plus b, then you get the resultant, vector r, you can see, right? But now I can look at everything in terms of then components and, even use the unit vectors. Because remember, I cannot add this a and b directly because they're both two-dimensional vectors. But here's what I can do. See, if I break it down, if I break down a into component, see, this is a, x component of a. Then let's take vector b. See, if I find the component x of vector b, this is that guy. This is bx. See, then this is rx, vector r, right? See, if I find its projection on an axis, on x-axis, I will see that this is that vector rx. Well, you can see, right, then this rx is equals to ax plus bx. So that's why I used that in the previous example, where sum of the x component of my vectors is nothing but the x component of the resultant. Same thing is here. This is ay, the y component of a. This is by, the y component of b. And this is ry, the y component of the resultant, which is equivalent to ay plus by. That's why I can do that. I can also use everything into their the component and a unit vector notation. See, vector a is ax I hat plus ayj hat. Vector b is bx I hat plus byj hat. And when I'm adding those two vectors together, right? So when I'm adding those two vectors together, see, those two, I can add them together because both of them are I hat. Those two, I can add them together because both of them are j hat. But I cannot add I hat and j hats together. Those are like apples and oranges. I cannot do that. But I can add all the x components and I can add all the y components, right?